Hello, this is Mr. White, and this video is on related rates part 1. I do ask that you get these guidelines from your textbook out in front of you as you go through the video and as you go through your initial assignments on related rates. You may read them right now and feel that they're not terribly helpful or you don't totally understand them, but I promise you these are the steps that we go through with related rates problems. Let's look at the 3 exercises we're going to do in this video. The first one is really just a conceptual look at a point moving around an ellipse. The second one is where we get into more detail and we actually do the related rates process as outlined in those guidelines. And the third one is where we look at a sphere that's growing and its radius is growing as well as its volume, and we want to relate the rate at which the radius grows to the rate at which the volume grows. So let's go back to the first one. And I'm going to go through these at a bit of a brisk pace where if you kind of have a sense of what related rates are about and you just need a few holes plugged in, I hope this will do the trick. But if you're totally clueless and you know you're completely lost with related rates, you're going to need to come into office hours and let's work that out. This video may not be enough to really lend any insight if you really have no idea what's going on. All right, so this first one, if the magenta point moves clockwise around the ellipse, discuss how dy over dt and dx over dt change in each quadrant. And again, this is not a really intensive number crunching type problem. It's more of a conceptual one, and its purpose is to see, do you understand what dy over dt and dx over dt means? So let's start by envisioning this point moving clockwise around the ellipse. Okay, ask yourself, let's look at the first quadrant. Let's focus on the first quadrant here. Ask yourself, as I go through the first quadrant, is x increasing or decreasing? Let's do that again. The x value right now is 1, the x value is 2, the x value is 3, the x value is 4. The x value is increasing, right? And meanwhile, the y value is 3. When I get to here, the y value is 2. When I get to here, the y value is 1, and then 0. So if you look at the x and y coordinates, we'll determine that x is increasing in the first quadrant, but y is decreasing. And let's think of what that means as far as dx over dt and dy over dt. Well, these are the rates at which x and y change with time. So if x is increasing, that means that for each little infinitesimal change in time, and time only moves in the positive direction. Time only gets bigger. So dt will always be positive. What about the infinitesimal change in x? Well, if x is increasing, that means we had a positive change in x. X got a little bit bigger. So dx over dt will be positive over positive, or we may simply just say positive. Similarly, dy over dt, again, time only moves forward. Time will only increment in the positive direction, so dt will always be positive. But the dy, if y is decreasing, that means that after this infinitesimal moment in time, the y value will have gotten smaller. So the change in y, the infinitesimal change in y will be negative. That means that dy over dt is negative. Get the idea? Let's continue down into the fourth quadrant. So what's happening to x? Increasing or decreasing? What's happening to y? Increasing or decreasing? See if you agree with me that x is now decreasing, but y is still decreasing as it was before. Therefore, dx over dt, if x is decreasing, that means that dx over dt is negative. If y is decreasing still, then dy over dt is still negative. Okay, I certainly welcome you to pause the video and complete the last 2 quadrants on your own just to test yourself, make sure you got the idea. I'm going to do them here real quickly. As we go through the third quadrant, we see that x is still decreasing as it was in the last quadrant, but now y is increasing. Y is on the upswing here. So x was decreasing and y was increasing. That means dx over dt, decreasing means negative, increasing means positive. And finally, as we go through the second quadrant here, x is increasing. It's a negative number, but it's increasing, and y is also increasing here. So that means that they're both positive, right? Again, the purpose of this is to make sure you clearly understand that this dx over dt, dy over dt represent rates at which x and y are changing with time. All right, let's take a more detailed look in exercise number 2 at this problem. Okay, given this same ellipse, we're given some information. We're told that the x value of the point is 3, which means that we could either be up here or down here. We're told that the y value is less than 0, so that settles it for us. That tells us that we're down here, right? If the y value is negative. And we're told that dx over dt equals positive 7. That is actually a useful clue for determining whether this point moves clockwise or in the counterclockwise direction. Again, dx over dt is a positive number. That means that x is increasing, right? X is increasing since dx over dt is positive. And that means that the point cannot be moving in this direction because x would be decreasing then. We must be moving in this direction, in the positive direction. So I'll put a little arrow there to denote that we've determined that this point this time is moving counterclockwise. We should begin to anticipate too. If you imagine the point doing this, is dy over dt going to be a positive or negative number when we find out what it is? Hopefully you agree with me that it's going to be a positive number because y is increasing as I go in this direction. Okay, so the dy over dt that we are to find, we're expecting a positive answer. We're asked a similar question for part B. We're probably not going to have time for part B. Let me move it off to the side and we'll figure out what to do with it. But let's figure out where we are in the 4-step process, referring to those guidelines that are from your textbook. Step number 1 says to identify all the given quantities and the quantities to be determined. Again, that was pretty much done for us. We were given these as equations. Usually in a related rates problem, they'll look more like a word problem, and you have to parse through those words and figure out what equations to write down. But they were just given to us here. We're also just told flat out, find dy over dt, and we are even given a sketch. So step 1 was pretty much done for us. Step 2 now, write an equation involving the variables whose rates of change either are given or are to be determined. So let's see what they mean by that. The variables whose rates of change are given, here's the variable whose rate of change was given, x, and the rate of change to be determined. Here's the other rate of change with variable y. So what step 2 is telling us is that we need an equation, and it's not a calculus equation, it's just a geometry equation or some type of more elementary math equation that involves x and y, that relates x and y. So let me move this off the screen, and just for time's sake, to keep this video from being incredibly long, I'm going to go ahead and provide you with that equation. And sometimes in our exercises, in our homework or on tests, you will sometimes be provided the equation. Sometimes you'll have to figure it out. But I hope rather than just taking this as a given, I hope you look at that and say, yeah, that kind of makes sense. Notice that if you were to plug in certain values, well, first of all, notice the similarity between the circle equation, x squared plus y squared equals 1. That would have been a circle centered at the origin. And notice that this is just the vertical and horizontal stretches of that circle. And notice that if you plug in certain values, so for example, if you plugged in 4, 0, that would satisfy the equation, and that would give you this point. And similarly, you could get these other points and convince yourself that that is a valid equation for this ellipse. Okay? So I just gave you that, and likewise, if we know that the x value is 3, we could just plug 3 into here and algebraically solve for y, right? So again, just for time's sake, I'm going to just throw that up on the screen, but trust that you see where this is coming from. Turns out the y value is a little bit ugly, negative 3 root 7 over 4. Okay, let me clean this up, and let's again see exactly where we are in the process. We have We said step 1 was given to us. Step 1 was provided to us. Thank you very much. Step 2 was to write the equation involving x and y, and that's, again, sometimes it'll be given to you, sometimes you'll need to figure it out on your own. Let's see what step 3 is. Step 3 says use the chain rule to implicitly differentiate both sides of the equation with respect to time t. That means do d over dt of both sides of the equation that we got in step 2. Okay, so step 3, let me clear up a little space here. Step 3, let's copy these two down here. And step 3 says that we are going to differentiate both sides of the equation with respect to time t. That means d over dt of both sides. Oops, somehow I lost the exponents there. Let me put them back in. D over dt of both sides. So we could do ourselves a favor if we want. We could rewrite this as, say, 1/16 x squared. Notice that's a valid rewriting, and you may prefer to do that. I'm just going to proceed with it written as is, but you may find that other option easier. Okay, so let's derive here. So if I derive x over 4 quantity squared, I'm going to need to use the chain rule a couple times here. I'm going to bring that exponent 2 down, power rule, and then I'll have x over 4 just to the 1 power, reduce that exponent by 1. Chain rule says I have to derive the inside function now. I have to derive that x over 4. And you may think of that as 1/4 x. It's the same thing, right? So when I derive 1/4 x, I get 1/4. And the chain rule says dx over dt. Again, that's like our implicit differentiation, which is a form of the chain rule. Because this t and this x were different variables, I needed to put the dx over dt at the end. Okay, let's do the same thing with the second term. So let's bring the 2 down in front. Now we have y over 3 to the 1 power. Take the derivative of the inside. That's 1/3 y on the inside, so its derivative is going to be 1/3. And then chain rule, dy over dt. And if I derive the right side of the equation, the derivative of a constant will always be 0. So let's see. Let's clean that up a little bit. We'll get, let's see, 2 over 4 over another 4. That's 2/16. That's the same as 1/8. So let's write 1/8 x dx over dt plus 2, 3, and 3. That's going to give us 2/9 y dy over dt equals 0. And I would say we are done with step 3 here. We've derived both sides with respect to t. All right, finally, step 4. Step 4 says, after completing step 3, substitute into the resulting equation all the known values from step 1, and then solve for the required rate of change. So solve for the dy over dt. So refer back to step 1, where we're going to plug in this and the y value that we found and the dx over dt, and then we're going to solve for this, okay? So running out of room here, but let me shrink this down. There we go, and let's start plugging in. 1/8 x, we'll use that x value of 3. dx over dt, that was given to us, that's 7 there. Plus 2/9 times the y value. And again, that's something that you could have solved for. I ended up just giving it to you. I hope you understood how you could have gotten that on your own. -3√7 over 4. dy over dt, that's the thing we don't know, so we'll just keep it there, treat it as a variable. And we now see that that's the only variable there amongst a bunch of numbers. So let's proceed to solve for that dy over dt. This here, that's going to give us 21 over 8. And this is a negative value. I'm going to move it over to the right side where it will become positive, and I'll simultaneously simplify it a bit. So 2 over 4 will give us 1/2. 3 over 9 will give us 1/3. 1/2 and 1/3 will give us 1/6. And with that root 7 in there, I'll have root 7 over 6. And again, it's on the right side now, so it became positive, dy over dt. Let's simplify that, or let's get the dy over dt by itself. Let's multiply both sides by 6 over root 7. 6 over root 7. And that allows me to get dy over dt by itself. And on the left side here, let's see, I can simplify a little bit. 6 over 8, or I shouldn't cross them out. I should just say 6 over 8. That'll give me 3/4. And that 21 there, I'm going to write 21 as 3 times 7, because that's all over a square root of 7, right? And so 7 over square root of 7, that's just going to give me a root 7 itself. So let's just write that as 3 times 3 over 4 will give us 9/4. And then the 7 over root 7 will give me root 7. That is our dy over dt. I know I'm not managing my space as well as I could, but I'm going to roll with it here. As a decimal, that turns out to be about 5.953-ish. That is the rate at which y is changing at that very point in time. Okay, we'll definitely discuss more in class as to what that means, because if you have no sense of what that answer is telling us, then we've honestly got a problem. All right, there was a part B to this, and for time's sake, I'm not going to do it, but I'll welcome you to do it. So let's do this. Reset the screen here. You now see part B is back up there on the screen, and if you're interested in trying this one out on your own, go for it. Pause the video at this point, because in just a moment I'm going to reveal the answer there. Okay, if you've done part B, then let's see if you got the same answer that I got. dx over dt equals negative 20 over root 3. Or you could write negative 20 root 3 over 3. All right, let's move on to the third exercise. Okay, we're told that the radius of a sphere is increasing at a rate of 2 inches per minute. And the important thing to get right off the bat is just because the radius is increasing at a constant rate of 2 inches every single minute does not mean that the volume is increasing at a constant rate. In fact, it is definitely not, and we'll try to get a sense of that in a moment. So we're asked to find the rate of change of the volume at one point in time when the radius is 6 inches, and then again at another point in time when the radius is 24 inches. And we will expect that the rate will have changed. The rate of the volume will be different at these two times. And then we'll explain why the rate of change of the volume is not constant, even though the dr over dt is constant. Okay, so let's get a sense of this. Let me obviously I can't draw a 3D image on a 2D screen, but let's do the best we can with this. Let's picture that we have a circle that's growing in radius of 2 inches per minute. So as the circle grows from this size and it grows 2 inches in radius to this size, notice that its area increased by this much. Well, let's take a look a little bit later in time when the circle is this big. And then it grows over the course of a minute 2 inches in radius to this size. And we see there that the area has increased now by this much. I trust you'll agree with me that this growth of area is less than this growth of area. So even though the radius grew by the same amount each time, the radius grew by 2 inches in each occasion, the area definitely grew by different amounts. And we can extrapolate that and think in 3 dimensions that we get the sense that yes, we can believe the volume will change by at a different rate as well. All right, so let's get into the, find out where we are in our 4-step process. Our first step is to identify all given quantities and quantities to be determined, make a sketch and label as applicable. All right, let's just move this down here. given quantities, we are told that the radius is increasing at a rate of 2 inches per minute. So 2 inches per minute. And what am I going to say is equal to 2 inches per minute? I hope you're not thinking just r, because we're not saying the radius is 2 inches per minute. That doesn't even make sense. A radius would be some number of inches. It wouldn't be given in inches per minute. We're saying the rate of change is 2 inches per minute. So the change in radius, dr, for every little incremental or infinitesimal change in time is dr over dt. That's what we're saying with that first statement. We are doing step 1. Let me mark that here. This is step 1. Okay, what else is given to us? Here we are told that the radius is 6 inches. And let's handle that as a separate problem from the 24-inch case. So let's just cover that up and focus on the 6 inches. That is just a straight radius there. That's not a rate. So we'll say r is 6 inches at a certain point in time. Okay, and that's what's given to us. Step 1 also asks us to identify the quantity to be determined. And in that case, we're asked to find the rate of change of the volume. So let's say that we will be tasked with finding the change of volume with respect to time. So we're not asked to find the volume itself. We're asked to find the rate at which the volume changes. Okay, step 2. Step 2 says to write an equation involving the variables whose rates of change are either given or to be determined. So let's focus in on this. That's one rate of change. Here's another rate of change, the one to be determined. And we need an equation that relates r and v. R and v. And again, this is typically just a geometry equation. This is not a calculus step. This is typically a geometry step. So move that off to the side. And sometimes you'll be given this equation. Sometimes it'll be considered obvious enough that you should just know it. Even though I think personally this is a good one for you to just know, you'll typically be given this one. I didn't give it to you here, but you'll typically be given the relationship between volume and radius for a sphere. Do you know what it is? Volume equals what for a sphere? It's going to be 4/3 pi r cubed. And bonus to you if you knew that already. All right, step 3 is to use the chain rule, implicitly differentiate both sides of that equation with respect to time t. So that equation that we just wrote in step 2, we're going to do d over dt of both sides. That's step 3. Let me divide this up a little more clearly here. And let's do step 3 over here. And step 3 would be to take that v equals 4/3 pi r cubed and to differentiate it with respect to time. D over dt, d over dt. On the left-hand side, not a whole lot I can do. I can write it as dv over dt if I choose. And I do choose to do so. And that, remember, that's what we're trying to find, right? dv over dt is what we were tasked with finding. Equals, and if I differentiate the right side, 3 times 4/3 will give us just 4. Pi r squared, because the exponent reduced by 1. And then the chain rule, aka implicit differentiation, says to put a dr over dt at the end. That was step 3, differentiating with respect to time. Step 4, after completing step 3, substitute in all the values that we established in step 1, and then solve for the quantity that we were tasked with finding. Okay, so let's scroll down a bit, and we're going to plug in what we were given. So let's do this. Step 4. Into this equation over here, we'll get dv over dt equals 4 pi. R in this case, R was given to be 6 inches. So let's put 6 inches squared. And then dr over dt is 2 inches per minute. So 2 inches per minute. And if I just crunch all those numbers, I'm going to get 288 pi. Take a close look at the units. Notice that this inch is being squared and then multiplied times another inch there. So that's going to be inches cubed, right? Inches cubed per minute. And that's dv over dt. And that was for r equals 6. That's how fast the radius or the volume is changing when r equals 6. Now remember, we are also asked to find the rate when r equals 24. Remember that? If I go back up here and I remove this box, we had r equals 24. The good news is we've done most of the work. So we don't have to do all this over again. We're just going to go to that final equation and plug in a 24 instead. So I just need to redo this equation, but plug in a 24 instead. So dv over dt in that case is going to equal 4 pi times 24 inches squared. dr over dt is still the same. That was constant. And I'll get 4r equals 24. dv over dt is going to equal 4608 pi. We see the volume is increasing much faster at that larger radius than it was at the smaller radius. Okay, that was related rates. The one last thing we have to do is part B, and that'll be fairly quick. I'm going to make sure that's pretty quick. Explain why the rate of change of the volume of the sphere is not constant, even though dr over dt is constant. Well, that goes back to an equation that we came up with in this process. Explain why the rate of change of the volume is not constant, even though dr over dt is constant. Let's look at this equation right here. If dr over dt is constant, notice that we are multiplying it by a variable, 4 pi r squared. R is varying throughout this process. So we see that if I multiply a constant times a variable, dv over dt is going to be a variable. And I'm going to, rather than write that out, I'm just going to leave that as my oral answer there to part B. If that r squared wasn't there, then we'd have a constant times 4 pi, which is another constant. That would be another matter. But it's the presence of that r squared here. That's what means that we have dv over dt is changing with r squared.